A structure for SO3 always confuses some people, so here we go. What I like to do is count my valence electrons first. Sulfur brings 6, oxygen brings 3 each, so it's 6 and then 18, which gives me a total of 24 valence electrons. Which atom goes in the center? The atom with the lowest electronegativity, which is often the atom that can make the highest number of bonds. So there's my sulfur in the center. Here are my 3 oxygens around it. I'm going to make connections between all of them, single bonds. That costed me 6 electrons. 24 total, so I still have to put 18 down. Anyways, 2, 4, 6 electrons in my structure. I'm going to fill my outer atoms so they satisfy the octet rule. Are you ready? 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. There's all my valence electrons. You would think I'm done, but I'm not, because of something called formal charge, or rather, just because that's the way it is, all right? The formal charge helps you figure out which atoms donated electrons to which other atoms, etc., etc. Don't confuse it with oxidation number, although it's just not the same as oxidation number, even though that's gaining and losing electrons in a different way. Anyways, it's the number of electrons that the atom brought. Remember, oxygen brings 6, minus the number of electrons that are lone or in lone pairs around the atom. In this oxygen's case, it's 6 for 6 dots, minus half the number of electrons in bonds. I like to call it valence electrons minus dots minus the number of lines. Anyways, it's a -1 for this oxygen. It's a -1 for this oxygen and a -1 for this oxygen because they're all the same. This sulfur has brought 6 minus 0 dots minus 3 lines, which gives it a formal charge of +3. Now the idea behind these Lewis structures is you want to minimize formal charge. Having +3 and -1 beside each other is a big faux pas, all right? So what I want you to do, if you have that happening in any Lewis structure, and especially this one, is to take a lone pair from the one that has a negative charge and move it into a bond. That makes the electron pair shared between the 2 atoms. First of all, that helps satisfy the octet rule for sulfur. This formal charge is now down to 0. This formal, I guess that's up to 0, and this formal charge is down to +2. Now here's the part that always trips kids out, because we talk a lot about the octet rule. But really, the octet rule only applies 100% of the time to carbon, nitrogen, oxygen, and fluorine. Sulfur is an exception. Sulfur can handle 12 electrons per atom. So, you shouldn't feel afraid to move 2 more electrons into the bond, or a different bond, I should say. This sulfur now has 2, 4, 6, 8, 10 electrons around it. Violates the octet rule. That's right, because sulfur does violate the octet rule. It's a complicated reason, but let me just say it's in the 3rd period, the 3rd row of the periodic table, and the octet rule just doesn't hold up there. Finally, I'm going to take these 2 electrons and move them in as well. This formal charge is now 0. This formal charge is now 0. And if I recalculate the formal charge on this sulfur, brought 6 minus 0 dots minus 6 lines gives me a formal charge of 0. Formal charges of 0 on all the atoms is the holy grail of Lewis structures, and we have just drawn the actual Lewis structure for SO3. It is a sulfur that is double bonded to all 3 atoms. Let me repeat. Sulfur violates the octet rule. That's why you're allowed to have 6 bonds to it, aka 12 electrons around the single atom. And that's the way it is. All right, best of luck to you guys.